identifying the region. The region has to be the projection back from the plane as the interior of this level curve, which is right here. All right? In other words, it's nothing but the region x squared plus y squared is less than equal to 4. Okay? It is nothing but this region bounded by the level curve right here. I want every one of you to agree with me on how to identify this region. So in order to find this region, I know it is solidly bounded by these two surfaces. So I have to find where they will meet. So I find the curve where they meet, which is a circle. But this is not exactly the region yet. The region is what is bounded by this level curve, which is exactly a disk, right? Which is exactly a disk. And as long as your intervening region is a disk, which system you want to go to? Polar coordinate system. So here is another thing I want to say. I know this is a double integral, so I have to translate this problem into a double integral. As long as I finish translating, what is left is to evaluate a double integral. Are you with me? So as long as I already agreed this is the double integral where I already knew the intervening function as well as the intervening region, the following work should be strictly a double integral evaluation. Okay? You don't need to worry about what's before this thing anymore. You just need to look at this double integral and evaluate it. You can use whatever tool you learned before. Okay? So this will be the general principle here. You can still get credits even though some of your intervening function is not correct or some of your intervening region is not correct. But as long as you can evaluate the double integral correctly, you can still get some credits. You know what I mean? So as long as you arrive at a double integral, forget about everything before. You just focus on this thing and use your skills to evaluate it. Okay? That with me? Yep. So if I'm looking at this double integral, I know the intervening region is here, and also I see squares and squares. I want to go for polar. All right? So I want to go for polar, and for this kind of regions, we're pretty smooth about it already. So it has to be between 0 and 2 pi for the angle, from 0 to 2 for the radius, and then I need to translate everything from x, y to r and theta, all right? So this is 16 minus 4x squared plus y squared, which in this case, I'm going to see r squared again, right? But never forget about this extra factor r coming out, dr dz. So in the end, I'm taking the integral from 0 to 2 pi, 0 to 2, 16 minus 4 r squared r dr dz. I think I do the following. Okay, so this is a double integral about polynomials involving r. So it's pretty straightforward to evaluate the double integral. Okay, so these kind of problems will be pretty typical double integral questions you will see in the future. Okay, you need it to extract the information and get your double integral yourself. Questions? Okay, so next I want to gather all the types of regions here. So now I have a y simple region, I have an x simple region. In the very beginning, we actually began from a rectangular region, but we can never really get into that because it's too simple. So we can indeed translate between x and the y simple regions. We can also translate between polar region and x, y simple region. So from 0 to 3, from 0 to the square root of 9 minus x squared, square root of x squared plus y squared, dy dx. So I want to evaluate this double integral. If I wrote my double integral in this format, which kind of region is this? It's a y simple region. X is bounded by two numbers. Y is bounded by lower function 0, the upper function square root of 9 minus x squared. So this is a y simple region. So if it is already written down in the y simple region, you can begin your evaluation immediately. Right? You can begin your evaluation immediately, which I mean is I want to find the antiderivative function for this square root with respect to y. Y is the variable. You can try to find the antiderivative for this guy. It is not straightforward. All right?
Yeah.
It is not straightforward. You can go to a big table of the antiderivatives to find the antiderivative function for this function. Okay? It is over there, but I'm saying I don't have to know that much. And also, we're closed book and closed notes. You're not supposed to go for the big table. So I can find some other way to evaluate this double integral, which is actually much easier than looking at the table. Okay? So I want to translate this one. Now I have several different directions I can translate. I can translate this thing into a X simple region. But imagine if you're doing that, you still have to find the antiderivative function with respect to X. It is equally challenging. All right? So that is not going to help you too much. Actually, it's not going to help you at all. However, I now have a polar region I can go. So I want to translate this into a polar double integral. So I need to find where this region is. Okay? So this region is going to be bounded between 0 and 3. Y is bounded between y equals 0, which is x-axis, and y is equal to square root of 9 minus x squared. But we have done this so many times. When I have this kind of function, it is just a piece of a circle. Or if you want to see it explicitly, you square both sides, you're going to x squared plus y squared is equal to 9. So this is indeed a 1/4 of the circle, because x is bounded between 0 and 3. So I have to look at the circle in this region. And also y is bounded between 0 and square root of 9 minus x squared. So y has to be also positive. So it's only 1/4 of the circle right here. Okay? And it is bounded between two numbers, lower curve and upper curve. So the integrating region is exactly 1/4 of the disk. Are you with me? It's 1/4 of the disk. And then I need to identify this as a polar region. If I want to identify this as a polar region, I need two angles and 2 radii. All right? I need 2 angles and 2 radii. So 2 angles here is from 0 to pi half, right? And 2 radii is from 0 to 3. So this is 3 and this is 0 to 3. And then square root of x squared plus y squared is going to be just r. All right? We agree upon r has to be always non-negative. So square root of r squared is just going to give you r. But I don't want to forget about one extra factor r here, so dr d theta. So as long as I can translate this into a polar region, I'm just looking at an integrating function r squared, which is extremely easy. It's much easier than what you dealt before. Okay? So polar, in a lot of cases, will give you quite some advantage, especially if you're dealing with circle, part of the circle, part of a disk, and also when you have integrating function where you see x squared plus y squared. So this kind of problems, you can use polar rectangle and polar coordinate system to gain a lot of advantage. So you can do the following. Okay? So in the very beginning, I already said this. So double integral and triple integral evaluation is actually the easier part. How to identify the region is really the key. Okay, how to identify the region is really the key. So I want to finish our discussion on polar rectangles by mentioning about this R simple region. So R simple region used to be a pretty big topic, but in this semester, we minimized this into a very small portion. So it's R simple region. So I will only introduce you what an R simple region is, and I will give you one question to practice, and that's about it. So remember, when I have a polar rectangle, I have 2 angles. Right? So I have 2 angles. The smaller angle is alpha, the larger angle is beta. And then I have 2 radii, the smaller radii A and the larger radii B. So R simple region is talking about the radius will change according to angle. So essentially, I don't have 2 arcs to bound this region. I have 2 functions of theta to bound this region. Okay? So this function is a function of angle theta. So it's h1 of theta. And this is a larger function with respect to theta, h2 of theta. And the region is bounded between two rays and two curves with respect to theta. Okay? So in the simplest form, if I have h1 to be a constant function equals a, I have h2 to be a constant function equal b, then that is exactly the polar rectangle we have been looking at. All right? So if I have these two functions to be both constant, then it is going to be reduced back to the polar rectangle. Okay? So if you have these two functions to be constant, basically you have two arrays and two arcs, A and B. So this is a special case for our simple region. Okay? So this is a polar rectangle. Okay? So the special case h1 of theta is equal to A, h2 theta is equal to B. If this is the case, you're back to the polar rectangle. But generally, I can allow the radii to change according to the theta. So if you can imagine, if I'm moving my ray from alpha to beta, the restriction on my radii is also changing. Right here, if I move from alpha to beta, the restriction on my radii is not changing at all. All right? It is always bounded between these two distances. Here, the shortest distance and the longest distance is also changing according to the ray you are moving. All right? So if you're moving, if you can imagine, if you're moving your ray here, the point within this region will be also changing. Okay? Where here you don't change the radii at all. Okay? So this is the polar R simple region. And in this case, the integrating function will be still changed from Rx y to R theta. And also, when I write down the double integral as h1 of theta to h2 of theta, and then f of R cosine theta, R sine theta, R dr d theta. Okay? So basically, I switch between A to B to from H1 to H2. Okay? So that's the only thing you need to worry about. So this is the R simple region. R simple region is a much more generalized type of region than polar rectangle. Okay? But in this class, we're not going to spend too much time on that. I just want you to know there are polar R simple regions. And also, I'll give you one example to practice. Okay, so I want to evaluate the following from 0 to square root of from 0 to pi divided by 3. From 0 to secant theta r cubed dr d theta. Okay? So immediately, as long as I have written down this double integral, you should be able to identify this is a double integral with respect to our simple region. All right? This is our simple region because, first of all, it is in R and theta variables. And theta is bounded between a smaller angle 0 and a larger angle pi divided by 3. Okay? If it is a polar rectangle, I'm supposed to have two numbers for the radii as well. However, here, these two are not two fixed numbers. They are also depending on theta, right? So the lower one is not depending on theta, but the longest distance is going to be depending on theta in the function secant of theta. So this is indeed a polar R simple region. Now with me, this is a polar R simple region. And I can begin my evaluation directly here. All right? Now with me, I can begin my evaluation directly coming from here. I can find the antiderivative for R with respect to here. All right? Which is essentially, what is the antiderivative for R cubed? R to 4 divided by 4. And then evaluating from 0 to R equals secant theta. So it's R equals 0 to R equals secant theta. Okay? And then this is equal to from 0 to pi divided by 3 secant theta then to 4 divided by 4 d theta. What is the definition for secant theta? 1 over cosine, right? 1 over cosine. So this is indeed from 0 to pi divided by 3, 1 over 4 cosine theta to 4 d theta. Then I'm stuck. I need to find the antiderivative function for 1 over cosine to the 4th power, which is pretty challenging. You can still go back to our big table to find the antiderivative function for 1 over cosine to 4, but it is not going to be pretty. Okay, it's not going to be pretty. So here is what I usually suggest. If you're looking at a double integral already written down explicitly, you can always begin your evaluation. Right? You can always begin your evaluation. But unfortunately, usually this evaluation is not going to work. Because if it will work, it will be too simple. Okay? Usually you have to look at this double integral and identify this region in different type. Okay? You have to simplify this double integral by switching between our simple region to some other type in order to identify the region again and evaluate a double integral. Okay? But you can always try to evaluate in the very beginning and see if there's a problem or if you can succeed. Okay? You can always try to evaluate in the very beginning directly. But here I cannot do that. I'm stuck right here. So I need to look at this region and at least sketch where it is. Okay? So here is what I needed to do. Theta is between 0 and pi divided by 3. So essentially I have a ray which is the positive direction of x-axis. I also have a ray coming from the origin with angle 60 degrees. All right? So this region is bounded between this ray and this ray with 60 degrees. Right? And the radius is between 0 and r equals secant of theta. So essentially I need to look at r is equal to 0 and r is equal to secant of theta, or is equal to 1 over cosine theta. Okay? 1 over cosine theta. So if you look at this equation directly, usually we have dealt with x and y equations a lot. Right? So if we have an equation to define x and y, we can easily graph what the curve is. We have not done so much for the polar equations. I can give you an equation involving r and theta. Usually it is not very direct to see what kind of curve it is. All right? Usually it's not that direct compared to x, y.